Welcome to part 3 of our computer graphics channel. So today we'll be dealing with circles. And so right now you can see on the screen there's a little pattern that we've drawn with multiple circles basically. So how it works is you have one large circle and then you use a random point on the circumference of that main circle to draw small arcs of other circles. So suppose the starting point is this red dot. You draw this particular semicircle sort of thing, and then from this point you draw the next semicircle, which is over here, and like that you keep moving on. So you draw from this point, you draw this semicircle, and that's how you get this flower pattern. Now the input to this particular flower pattern is simply the center of the big circle, basically like the main circle inside which the flower is embedded. You then have the radius of that same circle and a starting location, which is represented by this red dot. So giving you a live demo of what that looks like. um, we are first asked for the radius, so let's change the radius to around 300. The offset angle, I'm gonna give it as 120 degrees, and the center is gonna be 300 comma 300, and the output that you get is a much bigger, obviously, circle with the flower pattern embedded, and the starting point over here, the starting point is taken with relationship to this particular point, so 120 degrees down goes over here. So now how do we draw this particular flower? Let's look at the code. So the first thing that we do is we get the input, obviously, and then we go to the draw function. Now the draw function first figures out where that first starting point is based on the offset that you've given, and it highlights that single point using a red color circle, and it also makes a circle, the outermost circle. So this is using a function, user defined function called make an arc, where the is circle flag is 1, showing that that particular circle is a complete circle. And then as you would have seen in the flower itself, um, there are three there are sorry, not three, there are six smaller circles uh, within the large circle. So those six circles all start at a offset angle of 60 degrees. So once we have the initial starting point, we add 60 degrees, and every time we do that, we call the function called make pattern. Now what make pattern does is it finds the new center of the circle, which is basically this red point, which will lead to this, which will lead to this particular red point, which will lead to this point, which will then lead to this point, and so on. So that gives you your 6 points, and it makes an arc, and this arc has a extent of 120 degrees. So if you look at the complete circle, it'll be 360 degrees, but the part that's inside this main circle is just a 120-degree arc. And to get this arc correctly in position, we first figure out where the arc has to start. Now, as I told you, this particular point for the large circle, this particular point is the starting position. So suppose I wanted an arc of 90 degrees. It'll start from here and go in a counterclockwise direction, so it'll go something up like that. But that's not what we want from all of the embedded circles. So in this particular circle's case, the one starting at the red dot, so basically this circle, the starting point is somewhere here, because of which the starting point of the arc inside the circle will be over here at 120 degrees, and after 120 degrees it goes another 120 degrees inside the circle anti-clockwise. We continue and we repeat this for all six of the circles, and that's how we get this flower pattern. The code will be available on Pastebin for all of you to check. Next, we have the circle drawing algorithms.
All right, so one of the main circle drawing algorithms is called as a Bresenham circle drawing algorithm, which basically makes use of the symmetry that's available with circles. So what we do is we divide the circles into 8 equal parts. each part has a 45-degree angle. And the way this algorithm works is we figure out all the points that are required, all the pixels that we need to light up for one particular part. And since circle has a property of symmetry, we figure out all the rest of the parts without doing this similar calculations for all the rest of the parts. So how this algorithm works is, initially we start with uh, the y, we take a radius and we start with the y value equal to your radius, and we start with the first quadrant, upper sector of the circle, and we take x value as 0, and we start incrementing the x values and figure out the corresponding y values that are required for those x values. So the way we do this is using a decision parameter. We'll link in the description what this decision parameter is and how we derive it. So if our decision parameter is less than 0, we set the decision parameter to d. So d is a decision parameter. We set d equals to d plus 4 times x, which is the x value that we have in this loop, plus 6. And otherwise, we set the d equals to d plus 4 times the x minus the y value, the previous y value, and add 10 to this, and decrement y by 1. So this is basically used to decide whether we take y value uh, to the right of the current pixel. So y value is the same as the current y value, or is one less than the current y value. So that is how this algorithm works, and these xy values are repeated for all the rest of the seven quadrants of the circle.
For repeating the same points in the different quadrants, we just play around with the position of x and y, as you can see here and here, as well as the signs. So you'll have x comma y, then minus x minus y, x comma minus y, and minus x comma positive y. After that, you exchange y and x, and you repeat the same procedure. Now, after looking at the Bressenham algorithm, we also thought about what would our own algorithm do, and that is actually a very simple algorithm which actually checks whether a particular point is within the circle or outside the circle. And by doing so, if the point is within the circle, then we only increase our x coordinate, but if it's outside the circle, then we move the pixels down. So now giving you a demo of what these two algorithms look like. Yeah. So the image on the left is actually the Bressenham circle, and the image on the right is the really naive implementation of how to draw a circle, where it actually looks for every single point and decides whether to include it or exclude. Like, should the circle be should each pixel be inside that circle or outside the circle? It's as simple as that. Now, the actual issue that you'll be able to see is when we reduce the size of the circle. So suppose we give a 4
Radius.
pixel radius. Then what happens is that the Bressenham algorithm actually looks a lot more like a circle than the naive algorithm that we're using. But at a slightly higher radius, say around 15, um, both are quite comparable in the sense that both look pretty much like circles. Apart from this, we also carried out a very simple time test to see which algorithm actually took more time. And by our basic calculations and basic tests that we ran, the naive implementation, the one on the right, basically takes a few more milliseconds than the Bressenham algorithm. So the few more milliseconds to draw one single circle, which had a radius of around 10,000 or 20,000 pixels. So obviously, while drawing one circle, it doesn't make a difference, but when it comes to large scale circle drawings in like games and stuff like that, then it will make a difference because there are a lot of circles being drawn. Finally, we just like to show you the pattern that you guys saw in the beginning of the video, drawn with these two algorithms. So one circle drawn with the Bressenham algorithm and one drawn with our naive implementation. And there you have it. So here again, you see that the Bresenham algorithm actually looks a lot closer to what we actually saw in the beginning of the video, with the petals being like aligned properly, whereas the naive implementation actually kind of twists the image a little bit. So the 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 standing part over here is actually this sleeping part over here, and this petal corresponds to this petal, and so on. But yeah, that's it.
Thank you.
Thank you.